I'm Sandro Fiore from the Euromed Center on Climate Change in Italy, and what I'm going to present here is the ENES Climate Analytics Service. Basically, the CMCC is the national facility in Italy that works on, does climate research, and so in particular in our case we are working on computational aspects regarding climate, so pretty much on climate informatics at this moment. So I'm a data scientist and I've been leading the division over the last 4 years, and the division was previously led by Professor Giovanni Alisio, who is also here in the audience today. And jointly with him, I have prepared this presentation on the ENES Climate Analytics Service. So basically, this is a service that joins together HPC and big data. It is intended to be framework for climate data analysis. So before starting, let me thank Mohan and the workshop organizer for giving me this opportunity for giving a talk this year. It's the first time for me here in UGA. I'm very happy. And I want also to remind that in 2011, we were actually one of the recipients of the Unidata Community Equipment Award. And actually, we were, and I think, we are almost the only non-US institution that won this grant, and we're very, very happy. And we had a course at the University of Salento taught by Giovanni on HPC, and we taught our students about HPC, climate change, and Unidata software in order to do data analysis, to search and discovery of the data, and so on. So we're basically here in the south of Italy, and we basically run the division on advanced scientific computing, and in Lecce there is also the CMCC Supercomputing Center, which is directed by Giovanni, and that's basically our national facility. And this is the outline. I will briefly introduce the European Open Science Cloud Initiative, which is basically the context, the framework where the ENES Climate Analytics Service is basically living. And then I will introduce ECAS and EOSCAB, which is the project, the first project on the EOSC initiative that basically is aiming at providing the gateway for the European Open Science Cloud. I will then go to the detail of the core service of ECAS. So ECAS is the ENES Climate Analytics Service. ENES is the European Network for System Modeling, so it includes basically the European climate community at large. And the core piece of ECAS of this system is basically Ophidia. So I will go into detail of the architectural aspects, and so a lot of things, the operators, the workflow support, and so on. And we specifically address some key points that are related to the data approximate analysis, which is the key topic of this session, and how we deal with workflows, how we deal with the climate analytics experiment large scale. Then I will also introduce the ECAS lab, which is basically the virtual environment that we give to our end users, and it's pretty much a mix of software and tools, so it joins together, for instance, our ECAS analytics service threads and the Jupyter and so on. So we don't want just to deliver a service to our users. We want to deliver an environment where people can find data, can find tools, services, and so on. I would say much more user-friendly. And then some future work and conclusions at the end of the talk. So let's start with the EOSC, ECAS, and Ophidia. So that's basically the context. The European Open Science Cloud is a ambitious program from the European Commission that wants to deliver basically an open data science environment. So that's a long-term plan. It's about 10 years plan, and there will be a lot of initiatives that will be ongoing over next years in the EOSC. And one of these is the recently funded EOSCAB project, which is an H2020 project that is aiming to provide the gateway to the end users in terms of services, in terms of infrastructure, and so on. That's pretty much the infrastructural part of the EOSC, and also the the central point, the gateway for end users that are coming from different disciplines and want to use the European level set of services for doing data science. That's basically the main aim of the EOSC hub. And well, at the time we wrote the consortium wrote the proposal, we as MCC jointly with the German Climate Center, DKRZ, we submitted a proposal about just one piece of this proposal about the thematic service. So we submitted an internal proposal that is called thematic service proposal on the about the ENES climate analytics service. So we were endorsed by the ENES community, and well, we were ranked first out of 64 proposals, and that's why today in the EOSC hub project, ECAS is one of the 8 thematic services that have been approved and are part of the project. So here we see several components that are part of the ECAS, and also several services that ECAS will be integrated to, and that are coming from the European infrastructure. So that's pretty much the context, the EOSC hub, and the framework, which is ECAS. Well, ECAS, as I said, is a data analytics service. It provides a server-side analytics support for workflows and analytics experiment. So it's a data approximate analysis server. So basically, there is no more download and process at home. That was the previous approach. And well, ECAS is the service, ECAS Lab is the environment. And in this environment, you will find a lot of services like threads, or we can also exploit IDV for the visualization. And we, as part of the ECAS, for the I/O part, we rely on the NetCDF library, the C version, because we do a lot of I/O on our climate data, which are pretty much all NetCDF files. So an important point is that this framework is based on the Ophidia core analytics engine. So it's as I said, it's a service that includes a WPS interface, a backend engine, and the backend engine is actually Ophidia. This is an effort that we have been running in MCC since the end of 2011. So when the hype of big data was not very visible in the Gartner hype cycle. And well, we started quite in advance on this kind of topic. I will show you also the motivation behind this research effort. By the way, that was like a strategic activity that we started so early at MCC because we recognized the importance of having a big data approach, replacing somehow the client side or the more sequential ones that were available at the time. And well, it's I would say a very strong effort. It's a great effort. We have more than 300,000 lines of code, and about 3-4 people on average in the team that have been working on this framework since then. And as I said, this is an effort that we have been running CMCC, and well, the keywords related to this effort are basically that this is a server-side approach, analytics service. It provides a parallel approach. So we want to exploit not only big data paradigm, but also an HPC one. So we want to join HPC and big data, and the underlying layer, we are exploiting cloud technologies in order to move the entire framework in the cloud. So there are end-to-end mechanisms because we recognize the importance of having like workflow support in order to define our climate experiments. So we not only need just single operators, but we need a way to orchestrate, to compose and orchestrate all these operators into a unique experiment. So that's basically the approach that we followed. So at the time that we started working on this project, that was the workflow that we discussed with our climate scientists. So basically, for instance, for running a multimodal experiment, analysis experiment in the CMIP context, our end users at CMCC downloaded quite a lot of data for 20 models, for instance, from different data nodes in ESGF, terabytes and terabytes of data, several months to complete the entire data download. And then, with all this data on their desktop machine, they started trying to do some data analysis using desktop applications or client-side sequential tools. And that was really a nightmare for them, because they took like 6 months to run an analysis experiments, and 3-4 of these months were just related to the downloading the data. So that was quite significant for us, and that was one of the points to address in our study. So what we understood, that instead of having this download and client-side data analysis, we just moved the data analysis in the data center level, so close to the data facility, and well, trying to explore and to exploit also a parallel approach. So the dimension of the data was at that time already relevant. I would say that if we consider the estimations related to the CMIP6, about 20 petabytes of data that will be flowing into the SGF network, we understand that sequential approaches cannot give the proper answer for doing data analysis. So the approach was to deliver a server-side or data approximate framework with parallel capabilities. That was our key point to start working. And well, once we do all the analysis on the server side, then the output that was in general, based on our interviews with our scientists, was basically some charts, maps, and so on. So really lightweight. It's something that doesn't represent a big issue. So and users can do all their analysis on the at the server side, on the data facility, and then they can just download the final output, which is usually megabyte order. In terms of sites. And these were basically all the requirements that we collected, because once we explained the approach that we wanted to somehow implement in our division, well, the scientists, the climate scientists, started understanding the concept, and then they expressed much better the requirements about the data analysis. So initially they just wanted like average or subsetting. These were like the first two things, but once we explained the potential of the approach, they start saying, okay, we want to do model intercomparison, multi-model means, we want to write our own data processing routines, and then we need something that has to be efficient and extensible, so not only functional requirements, but also non-functional requirements. And then we started, as I said, working on this big data framework, and these are, in a nutshell, I will then go into the details of the framework, but these are the key points if I just would like to summarize in one slide what Ophidia is. So it's basically a big data stack for scientific data analysis, and it provides, it falls into the array database, from a database theory point of view, into the array database category. So it basically is well suited for doing time series analysis. And it starts from the database technology background, especially on the online analytical processing background, which is the kind of database technology that is used as foundation for the business intelligence. So much more in the market side. But if we consider that our data are mainly multidimensional, then we can see that the same kind of approaches in theory can be applied also to our data. Of course, a big difference with the climate science is that when we talk about climate data, we not only have data, but we also have metadata. And this makes a big difference with the tools that come from the vendors or from the market in general. And we'll see later on during the presentation that in terms of operators, half of them are for manipulating data, the other 50% is for metadata management. So we see how relevant is the metadata management in our scientific activity. That's why, also because market-based tools are usually not really well suited for doing analysis of climate, of scientific data. Well, we support complex workflow, which is directly connected to the topic of today. And well, there is simple API that allows the end users to plug a new operator or to plug a new primitive. I will then also explain a bit more what's the difference between operator and primitive. There will be some slides on that will be providing more details on this. And there are several interfaces because we expose this as a service. So in this regard, the interoperability is a key aspect because we want to build a community and we want to have users that can develop their own client applications. But in order to do that, we need to expose some standard interface, something that allows interoperability. And the OGC WPS is the interface that we are actually using. And in our community, it's something that is well accepted, I would say widely also accepted. For end users, there is a terminal that is the client application. It's really lightweight, is 1 RPM, few megabytes. Then you can install your terminal or your client or your desktop machine, and you can interact with the facility, cluster facility that we have in our center. So that's pretty much the approach. And from the end user perspective is in terms of developers, we support APIs both for C and Python. Even though, as was highlighted by Mohan, the Python one is the interface that we are really supporting quite a lot. C is the natural interface because the entire framework is written in C for performance reason. And that's why also because the NetCDF library is the C version. And the Python one is actually giving us a good flavor for end users to easily build end user applications. So that's basically, I want to say that until 3 years ago, we had quite very few end users developing in C for their own client applications. So I would say not so many. And then we started supporting Python with the PyOphidia class, and a lot of users are actually now trying to use our system or developing their own client applications in Python. Then there is support for batch and interactive data analysis, which is very important because we can like interact with the data facility, submitting one operator at a time and see what are the output, and then we can inspect the data, we can apply another operator and so on. Or we can submit a single job batch, like this could be like a processing chain that runs every night for producing some data. And well, the two modes are supported and actually can serve different use cases. So that's basically the paradigm. So we have our facility at the supercomputing center in CMCC in Lecce, and then the client application is just a terminal. It's a bash-like application, and the users can interact with the server facility, with the data analytics facility, just sending the operators that they want to submit. So I'm just sending the operator, but the real data analysis happens at the data center level. An important thing is that we provide the data cube abstraction to the end users. So the framework is able to manage multidimensional data, which we call data cube, and then all the operators that we support are basically data cube basic functionalities. So we provide an operator for doing data cube subsetting or data reduction or specific processing and so on and so forth. And that's very important because I would say that over the last few years, there has been a lot of interest in data cube-oriented technologies or projects and so on. So we're pretty much in line also with this kind of view. And the other important thing is that the framework is able to manage data cubes. So I'm not saying that it is only able to manage NetCDF data. So we were somehow in the design trying to have framework domain agnostic. So in practice, what we developed is, of course, is primarily serving the client community, and so it has a support for NetCDF, but in principle, it can manage all kinds of data formats that can be associated to a multidimensional data model. And that's an experiment that we did over last couple of years with some astrophysics group in the European level in the Indigo Data Cloud project. And basically we provide for the FITS data format a couple of operators in Ophidia, and then they were able to use all the other operators in our system just with these import and export operators that we provide just for their own format. Another important thing is that DataCube is not just about data, but is also about metadata. So we can attach a lot of information that could be the attributes that we have in SDF files. These are metadata information that we can attach to a specific data cube. Then there are metadata provenance information. If we want to see the provenance of a specific product, then we can retrieve this kind of information from our system. And then there could be a set of additional other metadata information that we could store, how the data is actually stored on the storage of our system. As said, we use HPC facility for managing our data, which means basically that once we import an SDF file into the system, we can partition and distribute the chunks of our NetCDF data across multiple IO servers or multiple nodes. And all this information about how we partition the data, how big is each chunk, and so on, are, again, metadata information, system-level metadata information. So as I said, the metadata part is really key, as we can easily understand. And it's not just about scientific metadata. And there is also much more than that. So, sorry. Let's now move into the first design architecture of Ophidia. So at the beginning, when we started, basically we started from scratch. As said, there were no big data tools at the moment, and I would say even less for climate. So the 3 points that we addressed at the beginning were basically the storage model, the primitive and the primitives and the operators. So I will mention all of them in the over the next few slides. So this is the first architectural design that we did, and that's basically the entire software stack. As said, this is a server-side approach. So here we have the server that exposes the front end to the end users. So once a client submits an operator, basically it goes through this interface. And then we have the analytics framework that is represented here by the compute nodes. So here is where we run the operators in our system. As I said, an operator is something that allows you to manipulate the data cube. If you want to do a subsetting, then there is a specific operator for doing that. If you want to do data reduction, there is another one, and so on. So anytime that you want to manipulate your data cube, basically you submit an operator that runs here. And this can be an MPI application. So you can have, I don't know, data reduction operator that runs on 64 cores, and then it does, basically, it triggers a set of primitives to the IO server. So here is basically where our data lie. So here is where we are storing our data and where we are basically providing the interface to our data. So these are the IO servers that do the real analytical job. So if I want to do data reduction, here is the engine that the engines that do the data analysis on the different fragments that are stored at the storage level. So for instance, let's imagine to have an SDF file. We can import, so we can send an import command to the Ophidia server. The import command runs here, and it creates, I don't know, 16 processes. Each of them triggers some commands to the IO servers, and each IO server takes care of a specific chunk of the NetCDF file. So that's how we implement the parallel reading of the NetCDF. And of course, all the parameters about the distribution and about the partition of our data cube can be set by the end users in the import command. So it's important that each IO server doesn't have the knowledge about the others, so the other ones. So what we can have at the level of IO server is really the control of just a single part of a data cube. And if you want to have the full view of a data cube, then here is the right level. So the operators are represent the right level for the data cube part. So I understand that it's a bit complicated, but if we go from the server front end to the data cube operators to the single chunks, then we can easily understand that this way is implemented to just, this approach is implemented just to have a sort of data parallelism in our workflows. So let's start from the very bottom and try to see what we have designed at the level of the storage, model. Well, I will not go too much into the detail of the storage model, but that was basically a two-step evolution of the star schema that we have in the online analytical processing database technology. And well, the important thing, I will skip just a few details, the important thing is that this kind of storage model is independent of the number of dimensions. That means that if you have basically data cubes with 3, 4, 5, or 6 dimensions, it doesn't matter. At the level of the storage model, you will always find some chunks that are designed the same way. So if you would be able to open the storage and look at the specific chunk, we will not recognize the dimensionality of the data cube from that piece of data. That's because the storage model is independent of the number of dimensions, and that's much clearer from this slide. So if we start from an SCDF file, which is a data cube, and then this is the classical DFM design, and then we implement the classical roll-up implementation from the database world, what we actually did were a couple of steps more for our scientific data, which are array-based data. So we basically, all the information about all the temperature samples were put on the same row for a specific lat-long point. So that's the way that we grouped somehow the data that were related to the same time series. That was the first point that we did. And the second one was to somehow get from the set of foreign keys here just a single identifier. So, as said, trying to skip some technological details here, what we have at the end is a very big table which exploits the key value approach, where regardless of the number of dimensions, we have just a key and the time series. That's basically the storage model that we have. And then from the storage point of view, we can split this large, big table into several chunks, and we can distribute these over a set of I/O servers. So as I said, there is a lot of background here from database technology, and I'm a database guy, basically. And so that is really, really important because that gives the foundation of the entire framework. And if this is efficient and well-designed at the very bottom, then we can get good performance also at the higher levels. And that's what we have in terms of virtualized or virtual file system in Ophidia. So since we have cubes, these are our new files somehow. So we have to deal with cubes. And so these cubes live into the cube space, basically. So we have folders, we have a set of cubes, and so the users can duplicate a cube, can rename a cube, can subset a cube, and so on. So everything is reflecting the data cube abstraction. Well, this is the I/O server part, and basically we have a set of I/O servers. In the back end of these I/O servers, we have what we call the primitives. The primitives are functions that work on time series, that work on arrays. So again, if we look at the primitive, basically, we have to somehow focus on a single fragment, on a single chunk of our data set. And then we can basically understand that this kind of primitives, these primitives are basically the end users analytics function that, for instance, do some time series analysis, calculate maximum, minimum, and other statistical indicators, and so on. And the important thing is that the primitives can be nested, so you can apply multiple primitives. There is an API for primitives, so basically that's the point where our end users jump in our framework and develop their own, for instance, time series analysis, because there is always a new functions that we are not covering. So we have about 100 primitives that we are supporting right now, but anytime we have our climate scientists that, okay, I want to write my own plugin, I want to write my own function. And the compression is, again, an example of primitive, because we transform a time series and just compressing it. And, well, that's an example. As I said, primitive is applied at the level of the I/O server. So we are just reasoning about a single chunk of our netCDF data. So here we have, for instance, the chunk, and we can apply the OPH mat primitive with the sign function. So basically, we want to get 1 if we have a number greater than 0, or -1 if it's lower than 0. And so if we apply this primitive, then we have this output, again, an array with 1, +1, -1. And this is the scientific, I would say, meaning of the primitive. So we start from 3 time series, and then we get this kind of outputs. And this can be applied to multiple chunks by the operator, because the operator is the one that works at the data cube level. And so it triggers this kind of primitive across all the I/O servers. That's basically one function, but there are several macros that you can apply for the same primitive. So even though we have 100 primitives, the functionalities are much more. Then another example is the box plot. We have a set of time series and we here and want to calculate the box plot, the 5-number summary for statistical purposes. And that's another example of primitive that we implemented. And again, let's suppose that we want to do several things and want to change several things altogether. And let's think, for instance, to have our data compressed on the storage. And so we can apply 3 different primitives. We can nest them into a single function by single call, by calling, for instance, first of all, the uncompressed primitive, because we need to uncompress the data. Then the subarray, because I want to calculate the box plot only on this specific subset of my time series. Then I need to do a subarray primitive in order just to take this part of the 3 time series, and then I can run the box plot on them, and I can get this kind of result. So as I said, the chaining of primitives is very important because you can do all of them in memory. So it's quite fast then for the calculation. There are also some vertical primitives, even though most of them are, I would say, horizontal ones. There are also some of them that are dealing with the vertical direction, and that's just an example. And for calculating the average across multiple time series, that's just a way to show that we deal with both the directions in the table, which are the only 2 directions that we can manage with this kind of data model. Well, what can we do in terms of operators in our framework? Well, there are several operators that we support. As I said, there are about 50. This is a set of functions that doesn't grow so much over time, because it's a sort of functionality that we can apply on data cubes, and we pretty much covered, I think, all of them. And there is a sort of algebra of data cube operators, so because you can like build a set of like an expression, just chaining several operators as mathematical expression. For instance, we can duplicate a cube, subset, reduce. That's just a way. I will show you an example in a few minutes. So this is basically the set of operators that we support. There are a couple that are for the import and export of the data into our system, and from outside our system. So the import is just the command that allows you to bring your data into the analytics framework. Once the data is stored according to our data model, then I would say it's somehow format agnostic, because it's stored into our system. So it doesn't depend on, I would say, any netCDF specific operation. We have a data cube to manage. We no longer have like netCDF file. That's very important, because we can apply the same approach for multiple data formats that somehow reflect a multidimensional data model. As I said before, when we added the support for the astrophysics, we just decided and implemented the import fits for the fits format and the output. Then, once the data is inside, the astrophysics were able to reuse the same operators that we're using for the analysis of the netCDF or climate data sets. And that's an important point, that it gives some flexibility and also extensibility of the system to other domains. And well, there are other operators that allows, for instance, to do intercomparison or to explore the data. So if we want just to have a look and get some insight from the data cube that's been produced, because anytime that you submit an operator, you don't get the data that are inside the new data cube. Because anytime that you submit operator, you generate a new data cube. But you just get the PID, the persistent identifier of the new cube. You don't get the full output on your screen. And then once you can keep doing your experiment by submitting a new operator and so on and so forth. So if you want to just inspect a specific data cube, then there are some operators that allow you to just go into a data cube and see, okay, I want to read this specific fraction of data just to, I don't know, do some check or something like this. So that's an important point because we don't actually move data across the network. So we generate a new cube or new cubes, and these cubes are just there on the server side. And also the sessions of the end users are stored on the server side. So anytime that you log in with your terminal, you can do an history, and you can get back from the server the previous history of your experiments. So that was something that led us to the concept of community experiments. So once you start doing running a set of operators, you have a session. And in this session, you can run a set of operators for doing all your analysis. And the session is a sort of Google Doc. So you can share the session with other scientists. And so they will find your own history, your own data. They can contribute, run other operators. So that's a way to go in the direction of community experiments. This is something that is not, that we, from a technological point of view, support. And in the CMIP6, it's something that we'll design with our scientists. We'll have a team of people that will do some multimodal analytics for tropical cyclones. And the team will work in the same session, will explore the same data, and will do this kind of experiment. So these are the, this is a graphical representation of the operators that we have. For instance, if we do a reduce over the time series and we get the maximum, for instance, we start from this fragment and we get this one. That's at the level of the fragment. So you can imagine that this is multiplied in a data cube over multiple fragments. And again, also vertically, you can do subsetting, we can split, and well, there are many other operators that allow you to, I don't know, duplicate a cube or to do other stuff. That's an example of the data operator that allows you to inspect a data cube. So you can run in the OPH Explore cube, and then you can get this output. That could be useful because from time to time, if you run like 3, 4, 5 operators, you want somehow to know if the data that you are producing are realistic or you are not doing something good. So the inspection of the data is something that's sort of validation during the analysis, and that's something that we use in interactive manner. So usually our scientists develop their own experiment by starting with an interactive session. They understand the flow, the set of operators that they want to put together, and then they translate these into a workflow, for instance. But the first thing is usually an interactive session because they have to validate that the sequence of operator is the right one. And these are some examples of metadata operators. We can get the schema. Here we see how the data basically the PID of the cube, the three-dimensional lat long time, and the source file. So this data cube started from this netcdf file, and other information about the distribution. So the number of fragments, the dimension of a fragment, if the data is compressed or not. So all this information can be useful. And well, there are other operators that allows you to get the provenance, for instance. And here we see that after submitting several operators, we can say, okay, what's the provenance of this product? And then we can easily understand that this starts from 2 different files that we compared, and then we did several operators. Of course, realistic experiments looks like this kind of tree. And one thing that is very good is that in the sessions, we can share also the intermediate data. And usually what happens is that starting from an intermediate product, scientists can start a new branch and provide new kinds of data products. So that's quite useful and important because each data cube is somehow tracked with a PID. So in case there are users that are doing experiments with the same data sets, they can also reuse the previous experiments, the previous products that have been produced and stored on the server, and then starting from them, they can do their own experiments. So that's a way to reuse and share the experiments and products that are run by our scientists. So what can we do with a set of operators? That's an example. Let's think, for instance, to have a data cube with the 64 billions of elements, and we can import this data cube in the initial netcdf file into our system. We can split across 64 fragments. Each fragment is 1 billion element each, and each fragment is a table with basically 100,000 elements over the time series and 10,000 elements, 10,000 rows. And that's basically the structure of all of that. And we want to calculate the maximum across these 64 billions of elements. So we don't have like a single operator that does this kind of analysis. So what we can do is to chain several operators. For instance, the reduce max basically give us the maximum over different time series and for all of these rows in the chunk. And we can imagine that this is performed over different chunks in parallel by multiple processes of the same frame, of the same operator. Then once we get to this output, what we can do is basically to run a vertical aggregation in the same fragment. And the vertical aggregation gives us the maximum at the level of a single fragment. So now what we have is 64 fragments with a single element. So we can easily understand that with the first step, we dramatically reduced the size of our data. So here we're just talking about very small data. And at this level, we have 64 elements. So it's almost nothing. And once we have these single element fragments, we can do a merge. And so again, we can get a single fragment with the 64 elements. We can do, again, a vertical aggregation and get the maximum. So it's a sort of risk approach where we have just basic building blocks, and you can build your own complex operators just pipelining or chaining together a set of operators. So what were basically the limitation of the first architecture, and what's the direction that we took? It was 2015, once we had the first release in place of the Ophidia framework. Well, basically we understood that besides the kind of experiments that we could develop, like the previous maximum macro operator, we couldn't do much more. So pipelining was okay, but what about having our own graph, our own workflow, our own experiment? So basically, what we learned at that time was the experiment from our scientists that this kind of support was actually good for interactive data analysis. But for batch analysis, where we have to design our own analysis experiment, we needed something more end-to-end support, something more in the direction of the workflow support. And that was the key requirement for the architecture version 2. Then the Python applications, because we understood that the C support wasn't enough for our end users. And then the in-memory analytics. So we wanted to move from persistent-based analysis to in-memory one. That were the 3 key points that we have been addressing over the last 3 years, and we've been quite successful in this. I will show you some results. So these are the kind of experiments that our scientists want to implement. They are interested in getting maps related to, I don't know, multimodal analysis or climate indicators or whatever kind of analysis they want to run. And in order to do something like this, we need different support, as I said. We need an end-to-end processing support, workflow support. That's why we extended the server front end in a way that actually now supports the the design and the runtime management of workflow experiments. That was really, really important for us. And I will show you some examples of experiments that we implemented. So the key points here were the workflow support. Basically, the key points was that besides the MySQL I/O server, that was the first legacy component included in our framework, we implemented the native I/O server, able to run in-memory analytics. That was really a major step forward, and this kind of I/O server is able to interact with different backends. For instance, object stores or RAM, the memory itself can be considered another kind of storage, and of course also databases. So while the MySQL approach was somehow not giving us so many opportunities to the storage level, the new native I/O server actually led us to new opportunities. And that's really something very important, because if we want to run, for instance, a workflow, we can run the entire workflow, maybe hundreds, thousands of operators, everything in memory. So you don't need to go like in memory and store the intermediate data cube again, over and over again. What we can do is just load the data in memory, run the entire workflow in memory, and store the result on the persistent storage. That makes a big difference with regard to the previous approach. So basically, workflow support it means that we need to have the opportunity to design things like this one, a DAG, less complex, more complex. It depends on the experiment, but something like this, where we have tasks and dependencies. Of course, we need the runtime, so we need something that helps us to understand that the workflow is running and that some tasks need to be running before other ones, and so on. So we need something that allows us to execute a workflow. That's what we call a runtime workflow management support. But of course, everything is not always green, so we need also to track like failures in our workflow. And I will not go into the details of this, but we have several policies for failures, because you can have a failure, but you can say, okay, this is not really relevant. You can keep working with this branch, or you can have a failure that actually is something very important, and so you have to cancel or to stop the entire workflow. Or you can even think, okay, this could be like a transient failure. So let's try 5 times or 3 times to resubmit the task and see if it was something transient or something that is really an issue in the way that we wrote the workflow. So that's a very simple way to say what kind of support we need for running some workflows experiment. And these are some examples of workflows that we implemented for, as I said, for doing several things. Climate indicators, most of them, or some operational chains that are related to fire danger. I will show a slide about that. Or other things that are other kind of experiments, multimodal in the context of the CMIP, for instance. And these are some examples. But if we look at this slide, what we can see is that, well, if I need to write my own workflow, what should I do? Should I describe all these tasks? So here I have 600 tasks. So should I write my workflow document with 600 tasks in it? So of course no. The answer is not. But what we can do to support easier, more lightweight description of the workflow is providing some constructs that allows you, for instance, to define a loop, to define, for instance, a condition, so you can have several different branches, and that's the kind of support that we added. For instance, you have the for loop, so if you want to iterate across several months, across several years, you can just define a loop. If you want to parallelize the execution of the loop, because the data are not dependent on each other on the different iterations, then you can say, okay, this is a parallel loop, and you can add like a macro saying this is a parallel. So you can parallelize it. So just adding a parallel macro in your for loop, basically you can enable the runtime to do all the branches, all the iterations in parallel. And the same can be, for instance, if you want to have like an if a conditional construct here, you can have that. That's important. For instance, once you want to submit your workflow, and you have several input parameters. So depending on the input parameters, you can your workflow can just follow a branch or another one. And well, by using this construct, the writing a workflow is really much easier. And for instance, these are 600 tasks at the runtime. But if you see the workflow document, the description is just 7 tasks, because this is just iterating across all the different years, all the different data sets that we have. So it's the same kind of branch that we have here for all the data. So the real number of tasks that we define in workflow is just this one. You can like 7 tasks in your workflow. And then you have a loop across, I don't know, 1,000 files, but that's not my problem. That will be the runtime that will generate 1,000 or several thousands of jobs per runtime. So this is a very simple example, climate indicator. I will try to go a little bit faster as time is running. So here we have like 2 different for loops. The first one is here on one indicator or the other one. So we have 2 for loops. One is on the TNX indicator, the other one TXX indicator. So here we have the TNX computation, here the TXX computation. And here we have another parallel loop on the different months of our data. So again, the real number of tasks in our workflow document is 1, 2, 3, 4, 5, 6, 7, 8, 9. And then it generates like, I don't know, 65, I think, tasks at runtime. That's another experiment that we designed just 3 years ago with our fire danger scientists. And that's basically, that was designed with them. So we used this kind of formalism that we have defined to say, okay, we start from 5 different atmospheric variables that we get from the output of the WRF model. And then we manipulate all of these 5 variables to build 3 different fire danger indices. And at the end, we have like a map generation. So we every night we take, and this workflow takes as inputs the output of WRF model and generate several maps, forecasting maps of fire danger indices in our region. That's used by the civil protection in in my region. And this is the runtime execution of this workflow. So as said, it's something that happens when every night we submit the workflow. There is also video YouTube for this. So another important workflow that I had in this presentation, because it's related to the multimodal topic of this workshop, is about an experiment that we ran in the context of the Indigo Data Cloud project. And here, basically, we started from 3 nodes in ESGF. And, well, we tried to run in a different way the multimodal experiments and trying to exploit the server-side approach. There was also a paper on Big Data 2016 conference on this topic. And, well, Indigo is a European project. I will skip some details. And we were representing the ENES community in this project. And this was the multimodal experiment designed with our climate scientists. And basically, the schema is very simple. And here we have the single model precipitation trend analysis, because this was a multimodal experiment on precipitation trend analysis. So this is the single model part of the experiment, where we compare the scenario, the official scenarios, and the historical data for computing the trend of the precipitation. Then we apply the same on the different models. And since the models are distributed, this is something that we'll do in parallel on the different sites. We'll see in the next slide. And then at the end, we compute the statistical analysis on the results of the different models here. Of course, we started from the approach that our scientists were running in the CMIP context. So basically, to run this kind of experiment, the current approach was to download all the data from the 3 data nodes, store them here, compute all the client-side analysis, and generate the map. Well, as I said, the download takes time, it's very heavy operation, network expensive, and so on. So in Indigo, we designed this with a lot of partners, about 20 partners in this project. We designed this architecture, and basically that's the result. So the user, we basically have the 3 data nodes and the server-side facility close to each of them. So because we want to do the single model part of the experiment close to the data. And then we have an experiment orchestrator, which is a scheduler, Kepler in our case. And the user just trigger this, the workflow to the Kepler. And the Kepler, again, in turn, triggers on the 3 sites, the single model part of the experiment. So what we have on each site is that the single model is basically a workflow in Ophidia. And once we run these in the facilities, Oak Ridge, Livermore, and CMCC, we get like an output, very order of megabytes, so very lightweight. We transfer these in Oak Ridge, and here we do the statistical analysis. That is the second part of the experiment, again, an Ophidia workflow. And finally, we send back to the user the map, which is kilobyte order. So we didn't move any data across the network. And basically, if we think that to do something like this with a client-side approach, our scientists took like several months. In this case, what we understood is that it will take no longer the couple of hours to do everything. So it's really something revolutionary that the full community is actually trying to foster, to address different tools and so on, of course. And what we have behind the scene, our workflow document. So that's JSON representation of the document. Basically, for each task, we can describe the related JSON representation. Of course, it's not easy to write a JSON task, but we're working on some user interfaces that will just do some drag and drop of the operators, will make transparent this translation. And well, if we want to submit a workflow, once we have the document of the workflow, from our Ophidia terminal, we have just to submit the workflow as a single command. So it's like an exe file, and so we submit the workflow, and then we get the answer. We can have a look at the runtime, and so we see that there are, for instance, 82 tasks, all of them completed. We can inspect the status of all the tasks. So we submit just a single operator, and then we can understand what is going on in the runtime execution. And of course, for each task, we have a label, and we can see the status. So it's really fine-grained for tracking the runtime of the experiment. So what can we do from a programmatic point of view? As I said, we do provide Python support, and so you can have like a class that allows you to develop your own application. And you can use, of course, Jupyter for doing that. So you can just import the PyOphidia class into the Jupyter hub, and then you can use it jointly with, I don't know, the other Python libraries. And well, the PyOphidia release was just released a few days ago. This is the latest, and this is an example of application. Basically, it's a Jupyter notebook. Then you can write your own Python application just using the different calls to the Ophidia framework. So here we see, for instance, that we instantiate the cube by doing the import. So we create a cube in our application by simply running an import of an SCDF file. It's important to say that at this point, the cube is created on the server side. It's not created on the client side of the Python application. So we're just saying here, look, I want to create a new cube by importing an SCDF file. Then I can run the subset operator here. And in this case, we are just subsetting our cube and creating a new one. And then the other instruction will follow. We have the matplotlib library for plotting the output. Here is just time series. And we do a conversion from Kelvin degrees to Celsius degrees by using the apply operator. So it's a way to just have a Python application with multiple operators. And anytime that we have an operator, here we have the import, subset, and apply. The Python application that is running on our client machine is just triggering on the server side an import, subset, or whatever is needed. Okay? So the Python application can be seen as a combination of lightweight client code with more heavy, I would say, server-side piece of code. Because, for instance, if I want to plot the time series, it's something that is happening on the client side, on the data that have been reduced on the server side. So it's a nice mix that is different from the workflow support where everything runs on the server side. Well, just a few things about the native IO server support. So this is basically a new I/O server that allows you to, I will skip some details here, allows you to run in-memory analytics. So as I said, in this case, the I/O server is able to run all the analytics in memory, so there is memory management piece of code, and it exploits OpenMP to enable some parallelism at the level of the single fragment. So once you process your fragment, this is done in parallel on groups of rows. And if we look at the entire data cube, we have that all the fragments computation is done in parallel thanks to the MPI level at the operator, on the operator side. So we have two different levels of parallelism. The first one is at the operator side, which is MPI based. It triggers several I/O servers. And once we are at the level of a single I/O server, then there is OpenMP to be more efficient on the analysis of a single fragment. And these are some performance results on the reduction on 128 cores with a dataset, 3D dataset of 375 gigabyte. With 50 billions of elements in total. And the nice thing is that with 128 cores, the new I/O server was able to outperform the MySQL one by 30 times. And that was a very good result. And now we are doing a full benchmark on the Athena cluster. Full benchmark because in our context, there is no standard benchmark for this kind of tools. So this is something that we have also published in a paper last 2 years ago. And that's the way that we do the import. Again, this is very too technical. And, but I want to just to explain the difference between the first version of the import that we had with the MySQL I/O server, with the second one, which is based on the new I/O server. So in the first version, the import relied on the MySQL I/O servers. So we didn't have any control on the MySQL server. So the operators, the import operator basically read the netcdf file data, and then it sent to the I/O server, to the MySQL, all the data. So there was this kind of data transfer from the file system to the I/O servers by considering the MPI operator of the import. So that was quite a bit inefficient because, of course, we had to move all the data into the MPI operator of the import, and then the import was able to send in parallel all this data to the I/O servers. Of course, we were parallelizing the I/O on the I/O server, but there was 2 steps in this kind of approach. So what we had with the new I/O server was that the import was moved into the I/O server logic, basically. So what we have is that the new import triggers on the different I/O server just the information about the chunks. So it's like that each MPI process here of the import tells to each I/O server, look, you have to import just this part of data. So it doesn't transfer the data from the GPFS file system. So here what we have is that this operator triggers to the different I/O servers the portion of data that each I/O server has to read. And the I/O server basically read the data from the storage. That's it. So there is no two-step process, two-step data transfer again. And that's why the new import is 10 times faster than the previous one. And the other point is that we also optimized the I/O phases by reading in larger blocks of data. That was an in-depth study of the netcdf library and some good strategy to read data in an efficient manner. So by the way, the new import is really more one order of magnitude more efficient than the previous one. So I will try just to summarize what ECAS Lab is in the EOSCAB context. So this is the environment. As I said before, ECAS is based on Ophidia and is the framework for data analytics. ECAS Lab is the environment where you have Jupyter Hub, we have an ECAS instance, you have threads, and Grafana for the monitoring, a lot of things that are in the same virtual research environment for our science. Of course, some functionalities are more for administrators, other ones are more for end users, but it's a good combination that allows us to deliver to the end users a single environment for doing research. And this is, in a nutshell, what ECAS Lab is. We have the Python notebooks, the file browsing. This is also available on Threads, quick start guide, monitoring, ECAS terminal. So that's, for instance, from the Jupyter Hub, what you can see from your account. You can run several notebooks. Some of them are already available in our ECAS Lab environment for training or testing. And this is the terminal that is embedded into the Jupyter. So you don't need even to run or to install the terminal on your desktop machine. You can do with your browser on the terminal that is available on the ECAS Lab. And then from Jupyter, you can run all the commands there. And this is the real-time monitoring with the Grafana. It's important. And besides monitoring, we also do accounting, which is important in the EOS Hub because we'll be paid based on the accounting information. So this will be the way to contribute to the European infrastructure. So and also to be sustainable in the future. And looking forward, well, two things. We're working on the workflow IDE, so an environment for developing your own workflows, and so you can take operators from here and you can drag and drop and design your workflow. That will be much easier than writing the JSON document. And of course, this is not an editor; it's an integrated development environment because you also have the runtime here, so you can monitor this. And of course, you can get for free the translation in JSON if you like, but you are no longer required to write the JSON part. This is in alpha release, so it's not available yet to end user. So we'll spend probably several months to complete it. And as looking forward, we're trying to move in the direction of the predictive analytics by implementing some long short-term memory network for time series prediction. And we did something like this. So we implemented the primitive for training, another one for testing and prediction. So that's the way how we plugged this, plugged into our system, this predictive analytics functionalities into our system. And that's basically so it's a specific kind of recurrent neural network, what we implement. So it goes into the direction of the machine learning. Of course, this is like a preliminary stuff that we're doing, but I just put this slide just because there is also the machine learning topic in the workshop. So I think that some of you could be interested in this kind of topic. And what we did as an example, we took a data set that we had at CMCC and the Adriatic and Ionian region. We had like for 1 point observations and the output of the SunnyFS model. That is a specific configuration that we have at CMCC. And here, basically, we compared the prediction with the observation and the output of the model. And what is very interesting is that the orange and the blue line are respectively the observation and the prediction of the LSTM neural network. And here in green, we have the output of the model, which, as you can see, the output of the model, the forecast basically, has a larger error than the one that we are predicting with the machine learning. So that's something that, as said, we're still at the beginning, but it looks very promising, and there are a lot of potentials in that. And some useful resources. Well, I put some slides, then I will share the slides with all of you, so I will send them to the workshop organizers. There is the information about the website where you find, for instance, the virtual machine to run to the hands-on. And here is the download section of the website. And there is also documentation and specifically a quick start. So if you, for the hands-on, you could go through the quick start and just run all the commands that are, with the explanation, of course, provided in the quick start guide. That will be the easiest way to learn and to approach or to start with the Ophidia. And that's the quick start. So there are several informations, and you can just go through all of them to run the hands-on session. And well, for the VM, on the virtual machine, you will find information about, for instance, the Linux account of your virtual machine, the Ophidia account, because you will have on the virtual machine a full Ophidia instance. So of course, it's not very super efficient because it's running on a virtual machine, but you have the full stack. So you can do training on a single machine. And then you can just run the OPH term and log into the Ophidia service that is provided by on the virtual machine itself. Or you can go to the Ophidia lab. That could be the second step for the hands-on during the week. And you can register to the Ophidia lab, and that's the registration form. I will send you your credential, and then you will have our 100 course environment available for you for doing training. And that will be, I think, one step forward with regard to the virtual machine, because if you go to the quick start and then you go here to the Jupyter Hub, you will run the Jupyter notebooks that we provided for this workshop in your home. So there are 4 Jupyter notebooks, and this is just an example. I just went through all the instruction of a single Jupyter. And then if you need information about, I don't know, I want to submit a specific operator, the full documentation is available on the website. And I always have a look at the documentation, because for each operator there are a lot of features, so you have to, I don't remember all of them, honestly. So I go through the documentation for understanding what can be used for each specific operator. And well, there are some tutorials also on YouTube that we are updating, so this could be also useful, and some resources that I leave in the presentation for you. And here are some publications in case you want to know more about the framework, and pretty much the conclusions. I will not go through all of them. Basically, what we described during this presentation is represented here. And I'm just really proud to say that there is an official release, new release, that we had just this week, last week, sorry, is the Ophidia version 1.3 that can be used. And if you want to join it, that's like an open source effort. We're moving in the direction of community effort. So if you want to join, please just let me know. I will be around the whole week. There are a lot of things that we are trying to approach, cloud aspects, cloud technologies aspects. We want to containerize the full stack. We are doing something in this regard. The user interfaces want to do more on these, or framework aspects for those that want to move in that direction. So we really want to open this, and the ECAS direction is the first step, because that was an effort between CMCC and the German guys of DKRZ. And that's it for my presentation. Thank you so much.
Any quick questions before we get to lunch? And if you do, try to use the microphones that are at each station, since we are recording.
I had one.
Go ahead.
How do you manage security for your users when they have the ability to upload their own functions?
Okay, so 2 aspects. One is about the data, and one is about the functions. So in both cases, when we have like a new primitive, this has to be like plugged in the back end of the system. So somehow we have sort of control on the functions that we are including into the system. But this is not usually very relevant from a security perspective, because it's mostly related to the computation of data. What could be somehow affecting the security are, for instance, I don't know, workflows where we want to, I don't know, remove everything and so on. So what we did was basically to isolate the user environment in a way that users actually can work in their own virtual space without like doing any damage for the other end users. So here in our cluster, we have the similar account management of an HPC cluster, basically. So everything is well isolated. Each user has its own account. And well, for instance, the input data are on a read-only section of the storage. And so there is, for instance, no way to, I don't know, remove data that are shared across users. And the other point is that we don't allow end users to upload their own data set, because in principle, this is intended for big data experiments. So if you want, for instance, that we host your data, it's something that we do like offline. You just decide the data set, we download them, we prepare them, we do the setup all together. Once this is ready, basically, you will open somehow the experiment to your community. So that's how we approach basically the management of the data. Also because it would not be so much realistic to give the end users the possibility to upload the gigabytes of data. I think that will be really, this is not, I think, thought for this kind of purposes. For instance, for the CMIP experiment, we are downloading all the data for the precipitation across CMIP 5, and we'll do the same for CMIP 6, mostly because there is a strong interest from our scientists to work on precipitation, to do analysis experiment on precipitation. And so we'll be like a sort of hub, analytics hub, for CMIP 6 precipitation. So any users that will actually log into the ECAS lab environment will find the service, will find all the data for the precipitation from CMIP available, and we'll try to keep the consistency across, updates that will happen on the ESGF side. So that's the way that we're trying to manage data and functions in the back end. Questions?
All right.
Okay.
He'll be around for the Taking It Home session later this afternoon, as well as all week, if you want to ask him individual questions or consider more of this idea of data approximate
And
frameworks.
if you log into the FIDA Lab website and you do the registration, I will manage to send you the accounts for the hands-on or for the next days. Thank you so much.
All right, so that does take us to lunch. We do have a nice expansive time frame for lunch. Lunch can be had either here in the cafeteria. They do accept cash and credit cards here, or you can feel free to go off-site to any place in town, whether you have a car or walkable distance. We are scheduled to come back at 2:15. So if you don't mind, to get us back on schedule, we can come back at 2:15, since that is still an hour and 40 minutes from now. So we'll see you back here then at 2:15. Have a great lunch, everybody.
Thank you so much.
Thank you.
No. I'm gonna grab some first so we can get some.